Hello everyone. We have already seen what is magnetic flux. That is, it is a physical quantity which gives the measure of the magnetic lines of force which passes, the number of magnetic lines of force which passes perpendicularly through a surface. So the measure of that numbers is given by magnetic flux. Now here we will see that how when the magnetic flux changes with a particular coil, an induced EMF or induced current is produced in the coil, and that is known as electromagnetic induction. So what we are going to discuss now is electromagnetic induction. So in electromagnetic induction, there are a series of experiments which were performed by Faraday. So accordingly it is then he gave some laws on the basis of those experiments, which are known as Faraday's law of electromagnetic induction, and these are very important laws. So first of all, let us discuss the experiment. A coil is taken, that it be a circular coil, and suppose a magnet is also considered. Let this be the magnet. Let this be the north pole of the magnet, and this be the south pole of the magnet. So we have the magnetic lines of force from the north pole to the south pole outside the magnet, and from south to north inside the magnet. Okay. So similarly here also we can show as many as possible. So you will have a large number of magnetic lines here. They are the continuous line. I am not drawing the whole line, but they are the continuous lines which you will find here. So the density of magnetic lines of force at this region near the coil, near the magnetic magnet, will be more as compared to the far away places. Now when this magnet, suppose we consider this magnet, and this magnet is, say, moved in this direction. This is the direction in which it is moved. Okay. Now when the magnet is moved in this direction, whatever flux was linked initially, that is the number of lines of force which was passing through the coil, it will obviously increase, because you can see here at this region the numbers are, you can see here at this region the number of electric lines of force are more here, that is the density is more. Therefore this place, when it gets nearer the coil, the flux increases here. So whenever there is a change in flux, okay, whenever the flux changes, a induced EMF or induced current is set up in the coil. Okay, here also an induced current will be set up in the coil. Let this be the direction of the current. But you know, like you can see here, there is no source of EMF, but there is no battery which is connected to the coil, but still then we are getting the current, only because there is a change in flux through the coil. Okay, so the flux has changed, and therefore the induced EMF is developed. The word induced is used here because no actual source is there. The current which we are getting here is also known as induced current, because the induced current, because we don't have any source of current. Okay. So here we see that when this magnet having the north pole is moved towards the coil, automatically the current is generated without any help of a source, because no source is connected here. The current is induced here, so the word induced is coming. We call it induced current. Now the current is responsible for an EMF, so that's why EMF, that is the potential difference, must be there between the 2 points of the coil, so that the current flows through the coil. That EMF is also known as induced EMF. And we have the induced EMF or the induced current only because there is a change in flux. Now Faraday also have seen that when the flux is changing, that is when the magnet is in motion, it is coming towards the coil, there is a change in flux. The flux will increase, but if it stops, at the moment when it stops, you will find that there is no induced current, that is no induced EMF or induced current is there. That means the induced current or the induced EMF lasts as long as there is change in flux through the coil. Okay. Now, there is another option also, like suppose you consider the same coil, but this time let me draw it in a bit different way. Let this be the coil, and we have the magnet here, the same magnet we are taking. It has a north pole and a south pole, and this time we are taking it away from the coil. Now, because the flux linked is decreasing, whatever flux is linked with the coil, now the coil flux linked with the coil is decreasing. So that's why again there is a change in flux. It doesn't matter whether the flux is increasing or the flux is decreasing. We need to have a change in the flux. Whenever there is a change in flux, if the flux is decreasing here, then also a current will be induced here, and we again have this electromagnetic induction. That is, you can see here the current, we are again getting the current without the help of any source connected to it. So the current is known as induced current and the corresponding EMF is known as induced EMF. The generation of induced EMF or induced current in a coil due to the change in flux through the coil is known as electromagnetic induction, and the induced EMF or the induced current will last in the coil as long as there is change in flux through the coil. Now you need to understand one more thing here. The change in flux may be because of the relative motion of the coil or the magnet. That means here I have shown you the example where the magnet is moving towards the coil. It can happen that magnet is at rest and the coil is moving towards the magnet or away from the magnet. Okay, so both ways it is correct. You have to just see that there is a change in the magnetic flux. Reason may be the motion of the magnet or the motion of the coil or motion of both of them. So what we can say is, whenever there is a relative motion between the coil and the magnet, a current will be induced in the coil. Relative motion means the motion can be because of motion of either of the two or because of both of them also. Okay, so I hope this is clear. 2 points from this experiment, 2 points are clear. One, that whenever there is a change in flux, induced EMF or induced current is produced in the coil. The induced EMF or induced current lasts as long as there is change in current, as long as there is change in flux. If the change in magnetic flux stops, then the current will also stop. That is, there won't be any induced current or induced EMF, right? The next point which Faraday made clear in his experiment was the rate of change of flux. Because the flux changes, suppose there is a change in flux given by d phi in time dt. So the rate of change of flux will be d phi upon dt. And this value, the rate of change of flux, is actually directly proportional to the induced EMF. Induced EMF is represented by small e. So it is directly proportional to the induced EMF. That means the value of induced EMF will be decided by how fast there is a change in magnetic flux through the coil. Faster is the change, that is rate of change of flux, d phi by dt is more will be the induced EMF. I hope this is very clear to you. So by moving the magnet or the coil towards or away from each other, by increasing its speed or its motion, we can actually increase or decrease the value of the induced EMF. Depending on the rate of change of flux, there will be the value of induced EMF. If the motion between them, that is the relative motion between them, is less, so the induced EMF produced will be less. If the relative change in motion or the change in flux is more, then the induced EMF will be more here. Now, another important point that you need to understand here, which was actually given by Lenz, L-E-N-Z, Lenz's law. What Lenz suggested here is the direction of induced EMF or the direction of current. The direction of current induced in the coil will be such that it opposes the cause which produces it. Now the cause which produces it, suppose you consider here the first diagram in which the north pole is brought near the coil. So when the north pole is brought near the coil, so to oppose the north pole reaching near this, a north pole has to be produced here. So you can see that the direction of current is taken as anti-clockwise. So the direction of current is decided by the direction in which it opposes the cause which produces it. Like here you can see the north pole is moving away. To oppose the motion of the north pole, a south pole is created here which attracts the north pole to oppose the motion. So south pole will be created if the direction of current here is clockwise. So it is clockwise direction of current, and here we are getting anti-clockwise. So you can understand here very clearly that the value of induced EMF, the direction of induced EMF or current is such that it opposes the cause which produces it. Here the constant term here is 1, but we put a negative sign here. We write d phi upon dt with a minus sign just to accommodate the Lenz law in the Faraday's law. This minus sign is because of the Lenz law, where he says that the direction of induced EMF or current will be such that it opposes the cause which produces it. So I hope this is very clear to you. 3 laws are there. All these 3 laws are discussed, but still then I am discussing it in a bit different written format also. Let us see that. See, in the first portion it is said that whenever there is a magnetic flux linked with a closed circuit changes, whenever there is a change, an induced EMF and hence an induced current is induced in it, which lasts only so long as the change in flux is taking place. This phenomena is called electromagnetic induction. I hope this is very clear to you. Whenever the magnetic flux linked with a closed surface changes, an induced EMF or induced current is induced in it, which lasts as long as there is change in flux. Okay, so this is clear. This is the first point we have discussed. The second point is the magnitude of induced EMF is equal to the rate of change of magnetic flux linked with the circuit. So mathematically induced EMF will be given by d phi by dt. The minus sign is introduced by the Lenz law, which is here. This law states that the direction of induced EMF is such that it opposes the cause which produces it. That is, it opposes the change in magnetic flux. This is very, very important. According to the Lenz law only, we will be knowing what will be the direction of induced current. This is very important because in numericals also you will have to find the direction of induced current, and then you have to think about this Lenz law only. So I hope this is very clear to you, but still then if there is any doubt, you can put me the doubts. Thank you and have a nice day.